into our work. Let's begin with a motivating example. This example is that you have two distribution. The expectations are the same, but they represent different risks. This is particularly useful for risk management, and I think there's been a lot of text that mentions this idea. But I think in the context of machine learning, especially in large language model risk and memorization, this hasn't been quite been studied because most of the works are based on ratio and just directly maybe the average of the memorization. So the problem we are interested in is the memorization problem. For example, if for example you use some data to train a model, and then when you use the model, then you give some of the data, and it's be able to memorize the exact sentence or exact n-gram of the data. So one of the way to formulate is that the length of um, the length of the continuous consecutively match the word after the input. So how many words it's being able to memorize for each data. Um, let's uh, let's start with one example to show that if the ratio of that risk, or if the expected risks are the same, that means something, but it doesn't really. Sometimes it fails to capture the finer structure of the risk. So, for example, you have two cars. Uh, you have two cars. The first car is maybe has a broken uh, AC or something, and you want to rate it by 1 to 10. So 0 to 10. So 0 is the lowest score, 10 is the full score, and you rate it for 10 days. Uh, uh, so so it's like almost perfect. So you rate it maybe 9 out of 10 for the first day, and 9 out of 10 on the second day, and you do this for 10 days. So this is the first day. This is the 10th day. You have the point, and the average point. The average score is 9 out of 10. Of course, you rate it for 10 days, and the second car. So I'll put this car number two. Car has is perfect, except a wheel, a nut in the wheel is coming loose. So maybe so on the first 9 days. On this is 9 day. This car is perfect. So you rate it 10 out of 10. But on the 10th day, the wheel fall off, and you have maybe you have a 0 here. Um, uh, so on the first 9 days it's perfect, but on the 10th day a disaster happened. So it's a 0. And you compute the average score for the 10 days, it's still a 9. So what this means is that the two scenarios have the same average score, but they represent different. The structure of the distribution matters. For me, I will probably drive the first car instead of the second. But let's look at the distribution. So what I mean by skew distribution is so this is a score. And this is the density of the score. In this case, the first car is so this is average is 9. The first car has a distribution that looks like this. So so all the scores are 9. So that's not a problem. And for the second car, you have a lot of 10s, and then you have a 0. So the distribution looks like this. Uh, right. So the distribution looks like this. For this reason, but you know so the second one is a left skew distribution, and the first one is a symmetric distribution. But but both of them have the same average score. So this is what I mean. Just having this score is not enough to access the scenario. Um, in the and you can see why this translates to the case of memorization because for example the my input of this memorization is my input. So I have some kind of input data, and then this is my input data. For example, patient A goes to and this is my this is my input. This is my reference. So reference this true data. For example, hospital A, and for example, here's let's take some extreme example. His social security number and so on. And so this is the rest of the sentences. And you train a model with the data, and then after that you test the data with the model. So you put this input data in the model, and you have a memorization. So maybe hospital B and his and something. So the ratio of memorization really matter here because if for every sentence it's only be able to memorize one word after the cut. So after the input, for example, the hospital, and the second term immediately becomes wrong, and so that's one kind of that's one type of memorization with low ratio of memorization. Another scenario of memorization, which still has a low value, but is different, is that for some data it does not memorize at all. But for one data, it's able to memorize the entire thing for very long. So so to plot it, this is to say like. In the first case, maybe the model is being able to complete the one word after one or two or maybe several words after the sentence, but and it has low ratio. In the second case, for the skewed case, is maybe that the model does not remember anything for the most of the data, but for a small portion of data, it's taken the privacy or patent of that completely the complete well it's for small amount of data is leaking all of the privacy or all of the violating all of the patent of the entire data. Um, so this is in this case. So from the experiment, it shows that for at least for all of the models in our all of the checkpoint in our case, is that if we define so if you define n3 as the number of consecutive word match after the cut. What I mean by this is that you have a true sequence. So this is the everything before the cut is the input, and the reference is maybe I just use 0, 1, 0, 0, and you have so you have model output like this and reference output like this, and you count from the first digit. This is correct. This is correct. This is wrong, and then you ignore the rest of the part. So you only care about the so this metric only care about the consecutive match right average. of course, this is not the only way to quantify it, but this is the way that we quantify memorization in a lot of cases, and this is the way of getting the memorization with high good probability without much interrogation of the model. Um, well, yeah, this is following a lot of other work as well. So in this case, we did an experiment. So this is at the horizontal axis we have n pre, and this we have the density. So is the density of n pre, and and the distribution follows like this, in the most part, and well, for all of the checkpoint that we have in at least in our paper, is it follows like that. I'm not saying that everything will, but this is going to be very possible. So when we have distribution like this, this could have average here that's very low, but really there. So this means in small amount, in some small subset of the data, it's been able to remember for very long. So three things happen. If you have such skewed distribution, so basically three things happen. First is that we let's say, so the first one is that small sample. A small sample of data usually underestimates so the worst case. So well, of course, if you have a true population of size m and you take a population sample of size z, then there's a good probability that the sample maximum is less than the true maximum, right? The sample maximum cannot be larger than the true maximum in a finite population, because that's all you have. But in this case, in a skewed case, then this can get really bad. And for this reason, when we sample from when we do the experimentation of memorization in large language model, in many cases, if you just take a small example, there's a good chance that you find low memorization or no point of that memorize more than 3 words at all, and it happens for some probability, and you can simulate it. The second thing is you cannot use a symmetric test based on assuming symmetry. So test using symmetry, for example, t-test. This cannot things like that cannot be used, because when you compare two skewed distributions, sometimes it's like you're comparing distribution. So this is this distribution 1, and this is distribution 2. Sometimes you're thinking of comparing something like this, or maybe something like this. So this is 3, and you want to say something is larger than others. You cannot assume this symmetry. So you cannot assume the normality. So you need to use something else. For example, you can reparameterize this. So you can reparameterize, and second, you can use non-parametric method. So That's all possible, and we make comparisons. There's a lot of tests from statistics that allows you to do this, but not in the sense of normal, just not in the sense of normal distribution, but has been a lot of work related to it in the in statistical inference. So this is not the key point for our paper. And three, one might ask, why is this skewed? Like why is it is it like that? So this brings a very a deep question, because usually when you think of something exponential, it's sometimes associated with the dynamic of generation. And if you think of a large language model, you can think of a large language model as the sequential way of generating the next token. So in such process, it's easy to, and the NPRE is something associated with length. So in this case, it's easy to get some distribution if the generation follows some like independent the probability of filling the next token follows some independent properties. This will be covered in a video called the sequential decomposition of memorization. And so the second part is really like what is covered in some in some textbooks, and so I'm not going to cover that. And so, but I want to, for the rest of the time, I want to comment on why. The first point, like why small sample of the data underestimate the worst case, and what's the ratio, and why it gets bad when you don't have the true population, you only have a sample of the distribution, and how bad can it get, and can we and also given the true distribution, can you estimate the rate that you underestimated? So this is all possible. This is because. For example, I have 5 points. For example, so this is my population. My population only has 5 points, and my sample, which must be smaller than the true population. Well, not necessarily, but without replacement, I can select. For example, my population, let's call it M, is 5, and so this is really a simple case. My sample size Z equals to 3, so in this, chalk is not good enough. So I have the case M equals 5, Z equals 3, so I can take 3 points. For example, I take these 3 points. If I take these 3 points, the sample maximum will cover the true maximum. So this is the x-axis. But if I take these 3, it will not cover true maximum. And you can. And further than that, you can take the order statistics. What's the probability that the sample of 3 in 5 underestimate the maximum in the sample is less than the some quanta of the true data. So you can have probability like this. So you can have So all of the cases is that you select Z sample from M, right? So this is all the combination you can have without replacement. To have this, and on the denominator you can have. You can select from M, but not the top one. So M minus N, let's call it NK. So the case, the number of case top worst one counting the replication, and you can select z from here. So this becomes a probability that your sample maximum does not contain the top k cases. This will be this. But we don't just have 5 sample, right? Usually you have m is very large because this is a training. This is a training data, and this will be greater than 10 to the power of 10 to the power of 5 rows usually. Well, for smaller amount of training, maybe you have 10 to the power 4 or 3 or something, or even smaller. That's possible. But usually this is greater, much greater than the benchmark sample, because if you want to test some, for example, if you want to test the memorization of GPT, for a small, if a research group want to do that, the data you get is probably less than the amount of data that used to train the model. So you have m is greater than z, much greater than z, and it turns out that this is both combinatorically and algebraically kind of not proven but formulated, and that if m is much greater than z, then the sample from sample width replacement is close to the sample. The sample width replacement result replacement is close to the sample width replacement. I guess you can use the Stirling's formula, and then you can have the probability that the max of sample of z. So this is the order statistics so you have z independent sample if you do a width replacement. So you have the product of that have z, and the product of mass of one sample, which is just the sample itself, pre and pre, less than this is less than n. You have something like this form, and since it's a product, you can write it as I write it here, p of n pre to the power of z. This is close to this is not close to this, but this is close to the probability that the maximum sample without replacement. If you have the true population, you can do something like bootstrapping. So what this can do is that you can calculate what's the probability that you get you underestimate the worst case, or what's the probability that your estimated worst case lies in some intervals. So so I have we can plot it. We can compute it with some with some bootstrapping, or maybe we can also iterate for all the possibilities, and so this gives this. So this gives the horizontal axis is the impre. The sample mass. Of impre, and here we have the true value. In the base case is 15 or 16. I think it's 15, and then on the y here we have z, and for z, taking small value, for example, dz is just one value, then it's just the distribution of itself, right? the sample max is the sample max for one sample is just Excel. So it's just the very skewed distribution, and for sample like somewhere in the middle you have some probability of getting this true maximum, and the closer you get so this is from 0, 1, and well the arrow should be pointing downward then, and for 0, 1, and then this is C approaching M. You have something, every point is sampled, so of course the sampled maximum is the true maximum that in this case. This is basically iterating for all the sample and get the probability you get the sampled maximum wrong, and yeah, this finished our illustration. Yeah, and the next video will be to do the decomposition and something. Yeah.